This problem is going to be an example of a strong acid and a weak base, and I'm going to call this one number 1. And in this example, I'm going to have a container which has a strong acid in it, and I'm going to add to it a weak base. Okay, so my beginning information is I'm going to have 44.0 milliliters of 0.150 molar HCl, and I'm going to titrate it with 0.150 molar of ammonia, which is a weak base. And my Kb for the weak base is 1.8 times 10 to the negative 5th. So in the first problem here, as I'm going to begin with not adding any ammonia, so 0 milliliters of ammonia added. So really all that I have here is the acid, so that's 0.150 molar acid, which is the same thing as the concentration of the H+, and if I have the concentration of H+, I can go straight to calculate the pH, which is negative log of the hydrogen ion concentration, which is a pH of 0.824, very acidic, which makes sense, it's a strong acid. The next problem I'm going to have for you is what happens if I add 34.0 milliliters of ammonia? And I have to evaluate what I have at this particular point. So if I have 44 milliliters of the acid, that's 0.044 liters of 0.150 molar. So that equals to 0.00660 moles of acid. And if I have 34.0 milliliters of base, that works out to be 0.0340 liters, and its concentration is the same. And that works out to be 0.00510 moles of ammonia. Now, I have a limiting reactant of ammonia, so this is going to be an if table here. So the acid plus the ammonia is of course going to yield ammonium. So initially I have 0.00660, 0.00510, nothing for the product, and finally at the end I end up with 0.00150 of acid. All of the base is going to be gone, and 0.00510 moles of the conjugate acid formed. So if I have acid left over, I have an excess of H+, and this excess of H+ is 0.00150 moles of H+, and dividing that by the volume, 0.0780 liters, gives me a concentration of 0.0192 molar, and then figuring out the pH of that works out to be 1.716 my pH. Now, excuse me, a third scenario is if I have 44.0 milliliters of NH3 that's added. Now in this particular case, the amount of acid that's there is still the same, 0.00660 moles, right? But if I have 44.0 milliliters of base, that's 0.0440 liters, multiplied by its concentration of 0.150 moles per liter, gives me 0.00660 molar of NH3. And so in this particular case, again using an if table, if I'm starting off with the same amount of both reactants, at the end there's 0, and I have just the product, which is NH41+. So I don't have a buffer, I don't have any acid, I don't have any base left, I just have the conjugate acid that's formed. So in this case, the only way to do it then is to figure out what the concentration of that NH41+ is. Now, if I have 0.00660 moles of it, my total volume is going to be 0.0880 liters. That's going to give me a concentration of 0.0682 molar. Now, if that's going to be the concentration of NH4 1 plus, of course what the NH4 1 plus is going to do with water is make ammonia and hydronium. Well, in this case, then, this is an ice table. And, of course, I have to calculate Ka, right? And in this particular situation, I'm going to go through the process of figuring out the K. The Ka turns out to be 5.6 times 10 to the negative 10 using Kw and Kb, which is given to you in the problem. I'm going to assume that you know how to do that. And then you calculate a concentration of hydronium to turn out to be 3.81 times 10 to the negative 11, which gives you a pH equal to 10.42 as my pH. Now in this situation, I have the same number of moles of acid and base, and so this is essentially the equivalence point. This is the equivalence point. Okay. The final example for this problem is, what if I have 55.5 milliliters of ammonia and it's added? Well, again, as before, the amount of acid that I have in there is the same, 0.00660. If I have 55.5 milliliters, that's 0.0555 liters times its concentration. That's going to give me a value of 0.00833 of ammonia. Again, if you use an if table, here I'm going to have an excess of ammonia, which is going to be 0.00833 minus the 0.00660. This gives me a difference of 0.00173. However, I'm going to have 0.00660 moles of the ammonium also produced. Having both of these present, well, what I have is a buffer. And so the H plus concentration is going to be Ka, and the concentration of the acid, in this case it's the NH4, the number of moles of the NH4 over the number of moles of NH3. So in this case it's going to be, the Ka is 5.6 times 10 to the negative 10. The acid is 0.00660, and the number of moles of base, 0.00173. This gives me a hydrogen ion concentration that is equal to 2.14 times 10 to the negative 9, which is an pH that is equal to 8.670.